Yeah. So we'll learn about gradient descent, what exactly gradient descent is. We'll be learning about the loss function basically. What is the loss function in machine learning? Why do we have that loss function, and what are we supposed to do with that loss function? And that is where gradient descent plays a part. So we'll be learning about that part as well. And apart from apart from gradient descent, we'll also be learning about dimensionality reduction. So dimensionality reduction is this concept which allows you to understand, what are the most important features in your data set. Okay, so sometimes what might happen is that you might have n number of data points, like let's say 100, 200 variables in your data set. So in such cases, what might happen is that your requirement, or your boss might have a requirement which says that he wants you to plot a graph between, it should just be one graph with an x and y axis. So basically a two-dimensional graph. But then essentially what is going to happen here is that if you have almost 200 different variables or features in your data set, then it is practically not possible to fit all those 200 features as a one-dimensional feature on the x-axis, right? So usually you take your x-axis as your input and your y-axis as your output variable, or the y variable, and your x-axis is the x variable. Okay. So now if you have 200 different features, how am I going to fit all those 200 features as one point? Like how can I just fit it as one point on the x-axis? Not possible, right? So for that reason, we have something called dimensionality reduction. So it helps you to gather the essence of each and every feature, combine them all together into one particular feature. That is what is called dimensionality reduction. So we'll be seeing more about what dimensionality reduction is. We'll be going through a particular algorithm called the principal component analysis, and I'll also be explaining some examples as we go through this particular thing. Um, so yeah, and after that, once we're done with dimensionality reduction, I'll be taking I'll be taking up a project-based approach for certain things. Okay, so it's going to be more like understanding certain concepts through code and things like that. Okay, so we'll be looking at two different projects, very basic projects. Okay, so these are very easy and very basic projects which will help you understand, number one, what so you'll be able to correlate the concepts that we learned yesterday with the models that we will be learning about today. And we'll be covering linear regression again via code as well. Then we'll be going through random forest, and we'll just see about what exactly machine learning is, what types of algorithms come, what are the types of machine learning algorithms, and some examples. Okay, we don't have the time to dive deep into each and every algorithm, which is why we have created material. So once all the webinars are done, we'll be sharing these material with all of you so that you guys will be able to go through these particular uh, concepts. So it just makes things easier. Anyway, guys, am I audible to everyone? Because I just saw a few minutes back that Anvit said that I'm not audible. Okay, cool. Great. Cool then. So let's get started with the session for today. Okay. So I'll be sharing my screen just like yesterday, requesting all of you not to fiddle with the icons down there because it really distracts me and everyone else in the session as well. So let's just keep a smooth session, and also don't take any pictures or anything because I'll be sharing all these slides. Plus I'll be sharing many more slides that I've created along with a few professors and all that. So please don't take any pictures. I'll be sharing all of these. Okay, so yeah, cool. So let's get started. I'll be sharing my screen. Just let me know if you can share, if you can see my screen. Okay, yeah, I've shared my screen. Is everyone able to see my screen right now? Okay, perfect. Great. Sorry. Okay, so first of all, yesterday we learned about something called quantitative modeling. And uh, in the process, we understood that whatever we are doing in terms of predictions and all are basically just mathematical equations. So you're just manipulating everything. So there's no learning as such. Yes, the only time you're going to learn is when you're training the model, but that just is basically the optimization part again. So all of them are basically boiling down to mathematical equations and mathematical functions. So the problem here is that all of you might be wondering, where exactly are those models used and how are they used? Even yesterday, a few people asked me questions as to, like, where to use what model, which is why I gave an example of a modeling that I did with respect to coronavirus, the predictions of how many cases would be there. And I said that, we could possibly use an exponential function, because if you guys notice the graphs, it constantly kept going up and it was increasing exponentially. And if you guys remember, one of the common feature of exponential functions is that for relative changes in x, there's absolute change in y, right? Uh, yeah. So essentially, so looking at that, I went with the exponential function. So there might be a lot of cases where we can possibly use, where we can use different equations. But is there actually learning when it comes to machine learning is the question. So let's be very honest about that. There is no learning as such. So essentially, so what is machine learning, first of all? So in very simple terms, machine learning is this concept where you're giving some data to your computer. Your computer understands that data, and essentially the data that you pass in is basically numbers, usually numbers. And the computer understands that and understands those numbers and tries to form a relationship out of those numbers. Okay. And then using the relationship that exists within that data set, it tries to make predictions for the future data, the data that comes in the future. Okay. So that is basically what machine learning is. So now if you ask me, is there any learning part over here? To be honest, there is no learning part as such. Okay. The only learning part is that you're actually optimizing the solution. So with each and every data point that you put in, so let's assume you have 10,000 rows in your data set. Okay. So the 10,000 rows over here, if I just given one row of data, it's very less data for my computer to understand, for my machine to understand what exactly is going on here. So the whole point of machine learning is it needs to understand the underlying process. If you guys remember, we also read about this yesterday. So it's all about, understanding the underlying process. But now if I just pass in one data point, it doesn't make sense. How is the computer going to understand that particular process? It's not going to understand. So I start passing in more and more and more and more data. So now the computer is able to understand everything, because what is going to happen is that, sorry, the computer is going to understand everything as I pass more data points, because now it has more data to make sense out of. So it can optimize a solution. It can understand what exactly is going on the back end. Okay. So that's the only place where learning is happening. So learning is basically your optimization part. Okay. And when I say optimize, that's exactly what's given here as well. So it's like we say we're learning something when the performance is improving with our experience. So essentially now what is going to happen is that, as I mentioned, if we take just one data point, one particular row, the computer is not going to make sense, understand a lot of things. Guys, can you mute yourselves? Okay. Yeah. Okay, I hope all of you are able to see my screen, right? If you can see my screen, please type yes in the chat section. Okay, great. Cool then. So if you guys notice over here, it says that we're learning something when the performance is improving is improving with our experience. That's exactly what I was talking about. So if I just give one data point or one particular row from a data set, it doesn't make sense, because it's just one particular thing. How am I going to learn out of something? So for example, if I, as a child, I might have, told numbers in a random order, like probably when I was 1 or 2 years old. I didn't know that one came first, two came second, three came third. I might have jumbled the order up. But that was my first attempt, let's say. Only if someone corrects me or if someone gives me more data, am I going to know that I actually made a mistake, right? So when I know that I made a mistake, I'm at a position to correct myself. So now I might say one, two, but I might say four. I might not say three again. So although I've made a mistake again, the error has reduced. So I haven't jumbled all the numbers up. I said one and two in the right order, and I said four after one and two. So it's just, an example that I'm trying to give. So machine learning, if you try to compare it to people, it's like essentially how we learn. Okay, so we also learn only over time, over different experiences, right? So now some of you might have got 97, 98% in your inter or 12th, right? And if I ask you guys to go back to college and write your exams again, you might be in a better position to score, a 99% as well, because now you're used to that. Okay, your experience has improved. And that is the case with, that's the reason why people in the industry also give more money to people with experience, right? In terms of salaries and all that. So yeah, that is basically what learning is. So now what exactly is machine learning? So we just discussed about how machine learning functions in a very intuitive manner. So essentially our core goals in machine learning is going to be that we want to improve our performance over a task T. So let's assume our task over here is to do some prediction with respect to, let's say, predicting how many people are going to suffer from coronavirus tomorrow. Okay. So that is our task T with respect to performance measure P. So let's basically it's like an accuracy or something. Let's say, okay, let's say right now our accuracy is some A%. You want to keep increasing your, A percentage, and based on experience E. So think about the data set for coronavirus is that every day there's more data coming in, right? So it means that the more data that you have, the more better it's going to be to form your predictions. So the model that I create tomorrow will be better than the model I created today. And the model that I created today will be better than the model that I created yesterday. So it's basically like, I'm trying to improve my performance of task T over a performance measure P based on an experience E. Here, the experience is basically going to be the data that I keep getting, and performance is any accuracy measure. And my task is to understand uh, how many people are going to suffer from COVID-19 tomorrow in the future. Okay. So we just have a few more examples over here. Handwriting recognition. For example, in a handwriting recognition problem, the task is going to be to classify handwritten words within images. So you want to understand what word is being written, handwritten within the image that we have. The performance measure over here is that the percentage of words correctly classified. So we basically we have labeled what each word is, and we are also trying to predict it. And then we're trying to see whether the prediction and the actual result are the same. Okay. And then what we're trying to do is we're seeing how many of them are same and different. And then we're trying to find the difference, and we're trying to find the percentage out of it basically. Okay. A relative measure which tells us about, which gives us a basic idea about how much, approximately how much percentage of it is being predicted correctly and approximately how much of it is not being predicted correctly. And what is the experience over here? The database of handwritten words with given classifications. Exactly. So as I was saying, each and every word has its own, each and every word has already been labeled in a particular manner, which is what is going to help us understand whether the word has been predicted correctly or not. Now the experience over here is that we have a database of these handwritten words, like a huge database of these words. So it just makes it easier and more efficient to compute whatever we require from task T. So similarly, there's another example given. So you guys can go through this example once I share the slides with you guys. Uh, so yeah, essentially the primary aim of machine learning is to allow computers to learn automatically without human intervention or assistance and adjust actions accordingly. So exactly. So the thing is that the only way to help a computer learn automatically is when we model the solution in the right manner. And when it comes to modeling, it's always, always, always going to be mathematics involved. Okay. So most of the time, as you know, the problem right now in the industry is that a lot of people are not aware about these mathematical concepts, which is why people, although they know about how to use scikit-learn or some module like keras, tensorflow, py yeah, pytorch and things like that, people don't really take these people for jobs because it's just about implementation. Anyone can learn how to implement things. It's about understanding things from an underlying perspective. So always make sure that see, if you're starting out right now, if you're in your second year, third year, it's fine. But then when you slowly enter into your fourth year, try to make sure that you start focusing on a more mathematical approach to things as well. Okay. So I'll tell you why exactly I say this in the end of this session. Okay, I'll be sharing an experience that I've had after the end of this session. So yeah, so you'll understand why I focus and stress so much on the mathematical aspects. Okay. So why is machine learning important? Now, for example, let's assume that you own a company. Okay, let's say, okay, no, let's say, uh, let's just take the example of COVID-19. So right now, what is happening is that COVID-19 is spreading everywhere through various districts to various states. So the problem is that now the government is not understanding where exactly it needs to improve its, healthcare supplies, because now initially the highest number of cases were in Kerala, but eventually right now the highest number of cases have shifted to Maharashtra, and that's because uh, as time progresses the situations are different, right? And you need to follow the data. So now I have this data, and using this data what I can do is that I can try to understand how COVID-19 is actually spreading, and I can try to give a future prediction on which states are going to be the worst affected. And if I give this data to the government, if I give my insights or my predictions to the government, obviously the government is going to be able to understand things in a better manner, because they can start focusing on improving the healthcare needs in these particular districts or states. So yeah, I mean, that is why machine learning is important. It helps you get an understanding of the future perspective in the present day itself. Okay, so it gives you an understanding of how the future is going to look. It's going to paint a picture of the future for you in today's day itself. So that is the use of yeah, that's basically the use of this particular thing. Okay, that's the use of machine learning basically. And the use cases, where exactly do we use machine learning? We use it in various fields like manufacturing, retail, healthcare and life sciences, travel and hospitality, financial services, energy. So it's like, stock markets. You want to understand demand and supply of, retail products, and how to put forward cross channel marketing, targeted marketing. Healthcare and life sciences, basically, exactly, disease identification and risk satisfaction, something like that. And then travel and hospitality, you know how exact. So for example, Oyo and all these companies, what they do is that they say they have these hotels. Oyo is basically a hotel chain right now. Thing about Oyo is that they keep changing their prices every day and with respect to every user. So they try to understand what every user is willing to pay, and accordingly they bump the prices up and make it look like they're giving a discount and all that. So all those things again come under dynamic pricing. So it's like constantly price keeps changing. So you have a lot of uses of machine learning. It's just for you to understand what sort of use is required for you. So now machine learning algorithms are divided into four different types. Okay, you have a supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So each of these are different in its own way. For example, supervised learning is a place where you can actually perform a proper classification of things and all that, because what's going to happen in supervised learning is that your data set is going to be labeled. You know that your data is labeled. For example, let's say that I have a set of 10 points, and these 10 points, I don't know what exactly they do. Okay, I don't know what needs to be predicted basically. But what I do know is that I have these input variables. Okay, I take these 10 input variables and put it into a model. Try to understand what exactly is going on and all of that. Okay, in that case, since I don't have a label, it's going to be unsupervised learning, because Now I can probably cluster these values, the like values together. Okay, so I can probably form groups of values that are similar. I can cluster them. That is called clustering. But I don't know what exactly each of them corresponds to. So since I don't have labeled data, it's called unsupervised learning. Supervised learning, on the other hand, is that, for example, I have data that clearly states that if I have 1, 2, 3, I get 4. If I have 4, 5, 6, I get 7. So I know what my data is. I have data which is labeled in the right manner for me. So when data is labeled in such a manner, it's called a supervised learning. Now, what is semi-supervised learning? Semi-supervised learning is basically that particular part where you have a combination of both supervised and unsupervised data. It's a combination of the two, supervised and unsupervised. Okay. And what is reinforcement learning? So reinforcement learning is basically what how we learn. Okay. So what we do is that we have multiple shots at things, right? For example, when I was a student, when I was in like probably seventh grade or eighth grade, I loved math. Okay, but as time progressed, I started disliking it. But again, I realized the importance for math and math related subjects that I started developing an interest for it. So as time progressed with my experiences, although I started disliking math, I started liking it again. Okay, so it's like yeah, so I'm learning from my experiences constantly and I'm updating myself. Similarly, even when you get into a job, you're expected to keep your best foot forward. And when you get into a job, even if you're a full stack developer, you always need to make sure that you keep updating yourself with the latest technologies. So you're constantly keeping ahead, you're staying ahead of the trend. So again, you're keeping yourself updated, you're making sure that you become a better person in terms of learning different things. And again, another example is a self-driving car. Self-driving cars are not apt from the very beginning. They make a lot of mistakes and they learn over various experiences. So that is basically again an example of reinforcement learning. So we'll just see exactly what each of these things are in slightly more detail. Okay. So, supervised learning is basically applications in which the data comprises examples of input variables along with their corresponding target values or vectors. So that's what I said. So we know what exactly are our predict values that are supposed to be predicted, or our output variables, or our target values. Okay. So if we know what exactly the values are, or the target variables are supposed to be, then it becomes a supervised problem. Okay, supervised learning problem. Now, in supervised learning, you have two different types of problems. You have regression and classification, and common algorithms that support supervised learning are k nearest neighbors, n nearest neighbors that you can call it, or k nearest neighbors, whatever it is, naive Bayes, uh, decision trees, linear regression, SVMs, etc. So we won't be dealing with all of these algorithms, but yes, we would be dealing with linear regression, and we would be dealing with decision trees partly because we'll be covering something called the random forest uh, algorithm. So in that, we would be covering decision trees as well. Now coming to unsupervised learning. In case of unsupervised learning, what is going to happen is that you know your input variables, but you don't know what your output variables are. So you don't know what your target value is supposed to be. So basically, in such cases, the computer is just trained with unlabeled data, and then you start creating different groups. So you start categorizing the types of data into different groups. So this particular technique is called clustering, okay? And you can also use something called the association rule learning algorithms. So again, as I mentioned, we won't really be diving into these algorithms right now. Probably some of you might be working on these clustering algorithms during your internship. But yeah, I mean, we'll be just giving you a basic insight into a few of the algorithms, and rest of it would be on YouTube, you guys to learn through the material that we provide. Okay. Now coming to semi-supervised learning. As I already mentioned, semi-supervised learning falls in between the previous two learning techniques. Okay, because few instances have the labels and few instances don't. So in such cases, what we do is that we take those that have the labels and try to train them. Okay, and what we do is that we try to build the best possible model out of the few that are present in terms of uh, lack of labels. Uh, so that is basically what semi-supervised learning is. Coming to reinforcement learning, this is something we won't be dealing with at all because this is a separate concept on its own. It's a completely different topic. Okay, so it's going to be very rigorous, and this in itself require like 15 to 20 hours of learning. So it's one of the most complicated parts in machine learning, and that is why everyone is looking for people who are really good with reinforcement learning and things like that. So essentially, what you're trying to do is that, as I mentioned in reinforcement learning, you're trying to update yourself or the algorithm constantly with the experiences that it goes forward. So if it performs the right thing that is required, it is rewarded in the right manner. So it gets some, for example, if you, as a kid, you guys must have heard this from your parents. Do this, do your exams well, and I'll give you a chocolate. Probably something like that. So that is basically you being rewarded. Similarly, over here, uh, there's a reward over here as well in with respect to reinforcement learning. But the reward here is not something that's physical and you can see. The reward here is going to be more like that it's going to be more inclined towards appreciating the algorithm, improving the score of the algorithm. Similarly, if the required task is not performed, or if it's performed in the wrong manner, then it's punished. So the you reduce the points or something like that for this particular model. So this is just a picture of how it looks, how exactly. So age environment is basically the things that you come across, the experiences. The agent is the person. Okay, so with respect to the agent performs an action for an experience. If the action that the agent performed was right, the agent is rewarded. Else, you just tell that it was a wrong sort of thing, penalize the agent, and then you again go put it forward in a loop. So it's an iterative process. Okay. So do you guys have any doubts so far? Any doubts so far with what we've learned? Okay, great. What about the others? Okay, great. So I believe that most of you are able to understand what's going on, which is great. Okay. So okay, cool. So moving on. Yeah. So this is just graphical representation of how exactly what type of algorithms come under these things and all that. So you have four different types of machine learning algorithms, four different types of learning. So again, within supervised, you have continuous target variable and categorical target variable. So what that means is that, as I mentioned, there was a point that said that using supervised learning you can perform regression and classification tasks. So in terms of so regression is something that we use when you have continuous set of data. Okay, it's not like you need to predict yes or no. In case if it's yes or no, then you use classification. Okay, or if you have like three different or four different target variables, if you want to group it into some group or something, then you can use classification. But regression, it gives you a number and a range in which the number falls. If you guys remember yesterday also, we spoke about quantitative modeling, and in that we spoke about regression being able to give a range of values. So yeah, in such cases, we use regression. So essentially, we would be covering only more, supervised learning concepts. Unsupervised learning is something that any these three are something that we won't be dealing with because machine learning essentially does not really matter on. So machine learning is corely focused on, supervised learning. But yes, there are cases where you have unsupervised, semi-supervised learning and all, but we essentially wouldn't be dealing a lot with these things. We might be dealing with certain aspects of unsupervised learning like clustering, but that's going to be about it. Anyway, okay. So this is just a basic understanding of machine learning. Okay. So moving on, we have something called the gradient descent. Okay. So just give me a moment. Okay, so we'll just revise the concepts of linear regression again, whatever we learned yesterday. So in case of linear regression, what we did was that we had a set of points, okay? And what we did was we wanted to understand in what manner could we pass a straight line through these points in such a way that the square of the vertical distances between the point and the line is minimized. Okay, so our main effort, our main goal over there was to reduce the error. And in case we had any outliers, then we had to remove those outliers. And one example that we spoke about, if you guys remember, was that prediction of house prices. Like for example, depending on the square feet or locality, a lot of features, the house price might change. Right, exactly, that's what we're talking about here over here as well. So size in square feet and the price in $1,000. So depending as the square feet increases, the price also increases. Might not increase linearly, but then obviously it's obviously going to depend on locality and all that as well. But then if you guys notice, it's possible to draw a line through that passes through majority of the points, and it's allowing us to reduce the error or the vertical distance, the square of the vertical distance between the line and these points as well. So this is just an example, okay? And now, as I was saying, it's possible for us to draw a line which passes through majority of the points in such a way that we can reduce the vertical distance. So this is one particular thing, okay? This is one particular line that we can draw. On the other hand, this is another line that we can draw. So this is more like, a power function, okay? So you could possibly use a linear regression model, or you could use you could use a linear function, or you could use a power function over here. So so someone asked me yesterday, if I mean, how do we understand what sort of formula we need to use for what problems? So the thing is that I mentioned it yesterday as well, that your formula or your mathematical modeling depends always on your data set. So there is no fixed thing. So now I can use a linear regression algorithm for this, not a problem. But also I can use a polynomial line, a line that passes like this way. Okay, so in this way, if you guys notice, the error is obviously going to be much lesser as compared to this, and I'm able to predict more points. But the drawback with this is that since I'm fitting the line like this, my line obviously it's going to keep going downwards like this. Okay, so it's not possible for me to kind of extrapolate. So probably as the square feet increases, the price might be $400,000. Okay, but then that value is way above my line over here because my line is constantly coming down. Similarly, this line, I mean, I can extrapolate it to various points, and I can try to understand what the value will be even for values outside that particular domain. So always you need to remember what your assumptions are and what your limitations are. And only if you remember what your assumptions and limitations are, will you be able to actually create the right particular model for machine learning as well for your data set. So yeah, so we'll just go through what exactly machine learning is. We'll just revise what we went through yesterday. Okay. So yesterday we remember that we saw this particular formula that said, y is equal to b naught plus b1x. And the reason I said we use b naught b1 is because over here in this case we have only one particular formula, one particular variable in this particular case. So in case of theta, in place of theta you put the b's, and in place of h theta of x you just put the y. It's the same formula basically. Okay, same formula that we learned yesterday. So it's basically like your y is equal to b naught plus b1x. But over here we have only one x. Okay, what if we have multiple x values, multiple input variables? Then I would put b2, so it'll be like theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, so on. So if I have only one particular input variable, then it's called univariate linear regression. So basically a linear regression with only one variable as input is also called as a univariate linear regression. Okay, So if I have more than one particular input, let's say if I had, in this case, I'm only considering the size in square feet. If I also had something like locality, crime rate, etc., etc., I would call it multivariate linear regression. Okay, so you have two different types of regression: univariate and multivariate. Now, the thing is that we always, so whenever we're talking about linear regression, we're talking about, in fact, whenever we're talking about machine learning, our core funda should be to reduce or minimize the error that we get. Okay, so there's something called an error function. Okay, this error function is the, I'm sorry, this error function is the function that allows you to, you know, uh, understand how exactly this error is actually varying with respect to each and every input and with respect to each and every output. So you want your core uh, aim should be to reduce this error function, and that is where something called gradient descent comes. So we'll be getting to gradient descent in just a bit, okay? But before we go to gradient descent, let's just try to understand some more things over here. So now, in case of, linear regression, let's assume a linear line, okay, a linear function, okay, not something, not a not a power function, but a normal linear function like this. So in that case, I can obviously have multiple lines, right? I can have multiple different lines that are passing through these points, but the difference between each of these things is going to be the error, okay? So thing is that, if you guys remember, our core aim in case of linear regression was to reduce the distance square between the point, reduce a vertical distance square between the point and the line that is being drawn. Okay, that is our core aim, and we call it the error so far, and we will call it the error as well in the future. But a more, um, you know, a more if you want a proper term for that particular thing, you call it the cost function. Okay, so essentially our aim should be to reduce the cost function through the number of iterations. Through, as the data set increases in its size, we want to keep decreasing the cost function. That should be our core aim. Now we want to understand which line is the best line. The best line would be the line which has the least cost function or the least error. And that is what we're saying, the line that minimizes the difference between the actual and estimated price. So it's basically the error. So how is that equal to the vertical distance, you might be wondering? So if you guys remember yesterday, so now this line is basically going to be the line on which we make our prediction. So let's assume that for 1,000 square feet, the price on this is basically something around $250,000. But in reality, for 1,000 square feet, the value is actually $300,000. Okay, these are the actual values, and these are the predicted values on this particular line. So there is a difference, right? So we want to compute what's the difference between this, and that is basically going to be your error or cost function essentially. And our core aim should be to reduce that, not just for one point, but for all the points in the graph. Okay, so essentially, if you guys notice, what it's saying is that we need to choose the parameters in case of linear univariate linear regression. We need to choose our b naught b1 or theta naught theta 1 and h naught in such a way that the the difference is, as I mean, we're able to reduce the values, reduce the difference as low as possible, because, and it should be as close as possible to y, which is the actual value of the data set. Okay, data that you have. So that is where we come across a function called the loss function. So if you guys noticed, I constantly kept saying that, we need to reduce the error, and the error is nothing but the square of the vertical distance between the actual and the predicted value, right? Or the predictor and the actual value. It doesn't matter, because since we're squaring the term, it's always going to be a positive term. So we do that, okay, and we take the average of all of that. So when I take the average of all of that, it gives me something called the loss function. Okay, and Our core aim should be to our core aim should be to reduce the B0 and B1 in such a way that sorry, our core aim should be to reduce the loss function or the cost function or the error in such a way that we keep tweaking our B0 and B1. And this is where we actually come across something called gradient descent. Okay. So now, in case of gradient descent, what is going to happen is that your loss function is always going to follow a curve like this. Okay. Guys, can you mute yourselves? I see that some people have unmuted themselves, so it would be great if you can mute yourselves. Okay. So yeah, coming back to this. So as I was mentioning, yeah. So we have our losses are going to be in such a manner because if you guys remember yesterday, we were also talking about something called the normal distribution. So the normal distribution curve is not exactly like this. It's going to be more like this, right? It's going to be something like this. But over here, if you guys notice, since it's a random process, obviously the errors are going to be on both sides of a particularly symmetric curve. And this is usually what is going to happen. Okay. Not always, but usually. And what exactly is gradient descent? Okay. So in lot of times what is going to happen is that you're going to have various graphs, right? You might have a graph that is like this. Okay, wait 1 second. I'll just see if I can draw it somewhere. Uh, so if I just give me a moment. It's just that I want you guys to understand this in a better manner because gradient descent is the most important concept in machine learning. Okay, cool. So let's just take this. So we might have a graph like this. Okay. Or we might also have a graph. So over here, if you guys notice, there's only one minima, right? Only one particular minima. But in case of graphs like this, you have multiple minimas. This is one minima. This is one minima. This is one minima. This is one minima, and this is one minima. So if you, so I guess most of you would have, gone to either Chaitanya, Narayana, or something like that for your inter. Um, So I'm pretty sure you guys must have learned the concept of maxima and minima, right? So over here, if you guys notice, each of these minimas, they are the local minimas. But so we can have multiple local minimas, but there's only one global minima, and that global minima is this particular part, right? So our aim at gradient descent is that we constantly keep iterating and differentiating a particular value, the cost function, to see where exactly our global minima lies. So the gradient descent function is to the gradient descent's main aim is to direct you to the global minima. Okay. So to start off with, let's take a very simple curve. Let's take this particular curve. Okay. It has one minima. Let's assume that this local minima is also the global minima. So what is going to happen in this case is that your so as your in gradient descent, your main aim is to keep reducing the cost function. Okay. And uh, cost function is nothing but the error as well. So what's going to happen in that case is that when I'm constantly going down like this, okay, when I'm constantly decreasing the values over here, it keeps going down. Okay, so I now again, one important point here is I can constantly keep varying my values and keep going down the curve, but how much do I go down the curve by? Okay, and that is where the concept of learning rate comes forward. What is learning rate? So you represent learning rate by alpha. Okay. And this term alpha is extremely important, especially when it comes to deep learning. Okay. So this is called the learning rate. Okay. We call it the LR or learning rate. Okay. So the learning rate is the thing that decides how fast or slow your algorithm gets trained. Okay, so essentially what happens is that, as I said, your main aim is to reduce the error. Okay, so so let's assume this is a graph. Sorry, 1 second. Yeah, so let's assume I have a graph like this. This is error. Okay, this is my E, let's say, and this is the number of iterations I have. Okay, and gradient descent, what it does is that with respect to each and every iteration that I do, my error keeps falling. Okay, and finally it reaches a stagnant point. Okay, so this is where I know that I need to stop training my model. Now you might have different curves. Okay, probably your curve is coming like this. In this case, what is happening is that your learning rate is too slow. Okay, because your what is learning rate? Your alpha value. Why am I saying it's too low? Is because this particular error is decreasing very slowly. Similarly, in this case, I might have something like this. In this case, my alpha is very high. Okay, or my learning rate is very high. Okay, alpha is much, much greater. But essentially, my learning rate should be in between these two. It shouldn't be too fast. It shouldn't get the curve down too fast. It shouldn't get the curve down too slowly. It should be in between these two. And why is the learning rate important, you might ask? So this is something we'll be covering in deep learning, okay? Because in machine learning, there's not a lot of importance of alpha, but in deep learning, you have something called hyperparameter tuning and all of that. We'll just discuss those things in brief when we for the AI people once we go into the sessions tomorrow and day after. Anyway, so yeah, gradient descent's main aim is to constantly reduce that error. So coming back to the slide, so as I said, if you guys notice, we might start off at a very high error rate and we constantly keep coming down. So we might bounce back here and there, to the other side of the graph as well. But finally, there might be a point where we come down, we come to this particular point. And over there, we know that it's our um, global minima, because we are going to different so in terms of minima and maxima, if you guys remember, even in inter, we always differentiated it and equated it to zero, and then we tried seeing whether it's the local minima or the global minima by checking the signs of it and all of that. And that is something that we're doing over here as well. Okay, so we do the same thing. And over here, if you guys notice, there's a term alpha. This alpha term is a term that determines how fast or slow the graph falls, or uh, yeah, how fast the graph falls, basically the error falls. So this is basically gradient descent. Okay, so any questions so far on gradient descent? Anyone? Any questions so far? Okay, how about the others? Okay, great. Cool. So most of you have understood the parabola where over here, this particular parabola. So see, that's what this is the thing that I've been saying since the beginning, right? So this is basically a curve of your error, like cost functions. Okay, so you're trying to constant. So these are the errors that you get for different points on your. So let's assume that you've plotted this particular line. 1 second. Yeah, so let's assume that you have these points over here. Okay, and then you have this particular line that you've put forward. Okay, you're now you have an error for each of these points, right? So that is the error that is being plotted over here on each of these points, and that is what is giving rise to a shape like a parabola. Because what is going to happen is that essentially your best fit line is going to be such a line which has equal number of points on both sides of the line. Okay, and the errors on one side, the sum of the errors on one side would be equal to the sum of the errors on the other side. So it's just a very intuitive thing, it's not a theoretical thing. Okay, so it's not like it has to become constant in the end. You need to find the place where the minimum error lies. Okay, so you need to find the place where the minimum error lies, that's about it. So it's not a constant thing. Yes, so when you're differentiating and all, yes, it needs to basically equate out to zero, and you need to make sure that that is the point that is your global minima. Okay, cool. So moving on. Yeah. So thing is that we've spoken about linear regression with one variable, but now we might have linear regression with multiple variables, and that is called multivariate linear regression. Exactly. So as I was saying yesterday, and even today as well, we might have multiple variables like these, and to predict the price of a house, like square feet, number of bedrooms, number of floors, age of the home, or various other things. So I'm sorry. In such cases, what is going to happen is that you have multiple variables, so it's called multivariate linear regression. So in this case, exactly as I was saying, your y is going to be equal to b naught plus b1 x1 plus b2 x2 plus b3 x3 plus b4 x4. So essentially, now if you guys notice, you can add all of these things in terms of vectors as well. So you can have one vector theta, okay? So you can have one vector as theta naught, and you can have another vector which is the x vector, which is basically a matrix of all the input variables. Okay, and yeah, so basically you've performed the same thing over here. It's just that the cost function will depend on multiple variables over here. That's the only difference over here. So now a very important thing when you come to machine learning is that machine learning, deep learning, everything is that you have something called normalization. So for example, in this particular data set over here, the example data set, if you guys notice, the range of values for each and every column is different, right? Now the problem is that when the range of values are so different with respect to each and every column, your algorithm might get confused. Okay, so your algorithm might not be sure what exactly does it need to do. It might be wondering what this particular thing means. So to give it a better understanding of things, we have something called normalization. So normalization is nothing but you turn in every value between every column in between 0 and 1. Okay, and that particular thing, how we do that is by taking the high yeah by we take the highest value and subtract the value that exists in every row from the highest value and divide it by 2 times the highest value. Okay, so you have various forms. So again, normalization can be done in different ways. So it depends on what particular range you want your values to be within. So you can obviously compute your own formula as well for normalization. But usually we have a few set formulae that we use. It, I'm sorry, and those are the formulas that will actually help you to convert these things within a particular range. Now, the advantage when you convert all the columns to one particular range is that when that happens, it just gets easier for you to predict the values. Okay, because now your model understands things in a more critical level, right? So normalization is one of the most important steps that is involved in any machine learning deep learning problem, and this needs to be done during the exploratory data analysis. Okay, so yeah, so I mean, I just want to talk about that, and learning rate is something we've already spoken about. So the reason I'm not covering all these intensive mathematical concepts is that I've already reduced these intensive mathematical concepts in very simple words. Okay, so I just wanted to make sure that you guys don't get overwhelmed by looking at all these intense mathematical calculations. Okay, so anyway, any doubts so far? Anyone, if you have any doubts, feel free to unmute yourselves or just put your doubts forward in the section, in the chat section over here. Okay, great. So, cool. So so now we'll be focusing on a more coding intensive part. Okay, uh, so we'll just be looking at a few projects, a few codes. Okay, and we'll see how exactly a machine learning problem needs to be tackled. And in the process, we'll also be learning about random forest, decision trees. Um I mean, most likely it'll be more towards random forest. We'll be covering decision trees within random forest, and we'll see how linear regression is actually implemented. So we'll be seeing two different problems, and then finally, after that, if we still have some time, then we'll be looking at certain other trivial things. Okay, I'll be explaining certain things like hyperparameters and what exactly those things are. Okay, so before that, let's just take a 5 minute break. Okay, just try to comprehend whatever has been done so far, and then we can start. We can resume the session. So let's take a break until 7:50. So let's take an 8 minute break. Okay, I'll just freshen up as well. I'll just take a few minutes of rest, and yeah, then we can start off with the session from 7:50. Okay, so yeah, cool. So I'll see you guys in another 5 to 10 minutes.